Comparing linear, exponential, and quadratic functions. Math of Mr. Williams. Example 1. Using graphs to identify functions. Tell whether the points appear to represent a linear, an exponential, or a quadratic function. So let's take a look at number 1. We have a series of dots. Let's go ahead and connect those dots to see what it looks like. All right, it looks like a U shape, so we're going to go ahead and call this one a quadratic function. All right, on to number 2. Let's go ahead and connect these dots. All right, this looks like an exponential function. We can see it is decreasing and it is approaching the 0. Okay, number 3, connect these dots. You can see it doesn't quite touch the 0, but it does increase. So it looks like this is also going to be an exponential function. And our last one, let's go ahead and connect the dots. See, this looks like a straight line, so this is going to be a linear function. Comparing linear, exponential, and quadratic functions. Math of Mr. Williams. Example 2. Using differences or ratios to identify functions. Tell whether each table of values represents a linear, an exponential, or a quadratic function. All right, let's take a look at the first one. We have x values and the y values. Let's go ahead and take a look at the x values. We see that they are increasing by 1 each time, heading in that positive direction. It's important. All right, let's take a look at the bottom one here, the y values. We see that it looks like they are decreasing. In this case, how do I get from 11 to 8? I'm going to take away 3. From 8 to 5, I'm going to take away another 3. From 5 to 2, take away 3. And from 2 down to negative 1, that's another minus 3. So these have first differences. And this function is a linear function. All right, on to B. Again, let's take a look at the x values first. We see that these are again going to have the same common plus 1 all the way across. That's really nice. Let's go take a look at the y values. We see to get from 1 to 2, we're going to add 1 here, add 2, add 4, and add 8. Well, that's not first differences. Now we could check those second differences here if we really wanted to. We could say, okay, how do I get from 1 to 2? We're going to add 1 here. We're going to add 2 on this one. And then to get up here, we're going to add 4. Well, that's not going to work either. So it has neither the first or second differences in common. So let's go ahead and erase that. And let's take a look and see what we have for any multiplication. So how do we get from 1 to 2? We're going to times that by 2. And then to go from 2 to 4, we're going to also multiply by 2. 4 to 8 times 2. 8 to 16 times 2. So these have a common ratio. So this table represents an exponential function. All right, on to C. Take a look at the x value first. We can see it again is increasing by that same amount of 1 each time. All right, but let's take a look at that y value. So we start with the first differences. So how do we get from negative 1 to negative 2? Well, we're going to take away 1. How do we get from negative 2 back to negative 1? We're going to add 1. From negative 1 up to a positive 2, we're going to add 3. Then from 2 up to 7, we're going to add 5. All right, doesn't look like we have a first difference. Let's try the second difference. How do we get from a negative 1 to a positive 1? We're going to add 2. Then from 1 to 3, we're going to add 2. And then from 3 to 5, we're going to add 2 again. Now in this case, this means it has a common second difference, and it means it's a quadratic function. Comparing linear, exponential, and quadratic functions. Math of Mr. Williams. Example 3. Using differences or ratios to identify functions. Tell whether each table of values represents a linear, an exponential, or quadratic function. We're looking at the first one here. We have our x values. Look like they are increasing by 1 each time. It's always important to check this. All right, on the y values though, let's see, we go from 0 to 0.5. looks like we are increasing by 0.5. From 0.5 to 1, we are also increasing by 0.5. From 1 to 1.5, we are increasing by 0.5 again. And from 1.5 to 2, we are increasing by 0.5. All right, so this one has first differences and is a linear function. All right, let's go down to the one below it. So we check to see about the x values, if they're increasing by 1. Looks like they are. 2 plus 1 is 3, and so on. All right, so we look at our y values. We see 2 to get to 6. We're adding 4. From 6 to 18, looks like we are adding 12. From 18 up to 54, we're going to go ahead and add 36. And from 54 up to 162, looks like we are going to add 108. All right, those are pretty different numbers. Let's go ahead and check the second difference now. So from 4 to 12, we're going to add 8. All right, from 12 up to 36, add 24. We can quickly see, so far it looks like first differences are out, second differences are out. So what we're going to do is we're going to go ahead and erase this, and we're going to check to see if it has a common ratio. All right, so what times 2 is 6? That's times 3. What times 6 is 18? Times 3 again. What times 18 is 54? Well, that's times 3. And 54 times 3 will get me 162. So it does have a common ratio. So that means it's an exponential function. Let's go to the one up here at the top. So we check the x values first. We can see they are, again, increasing by 1 each time. Let's go check our y values out here. So we're going to skip the adding and subtracting part here, and we're going to check and see if it has a multiplier. The reason I'm doing that is because I can see it jumps from 0.2 to 125 pretty quickly. So let's go ahead and map this out real quick. And what I like to do is I'm going to avoid that decimal right off the bat. I'm going to say from 1 to 5, I can see that it's going to be multiplied by 5. From 5 to get to 25, that is going to be multiplied by 5. And from 25 up to 125, that is times 5 also. So generally, this is going to probably be a common ratio problem. Let's go ahead and double check that point too. So what times, and if you think about this as money, 20 cents, okay? So 20 cents times what number is $1? That will be times 5. So this one does have a common ratio, which means it is an exponential function. All right, let's check our last one. So we go from -3 all the way up to 1 on our x values, so let's check that. We can see that's increasing by 1 each time. All right, let's check the bottom here. So we go from 2 to 4.5. It looks like we're generally going up in a consistent pattern here, so it doesn't make this huge jump. So I'm pretty sure it's not a common ratio, so we're not going to deal with multiplication. So let's check the subtraction parts. So how do we get from 2 to 4.5? We are going to increase by 2.5. And then from 4.5 up to 8, we are going to increase by 3.5. Then from 8 up to 12.5, we're going to increase by 4.5. And then from 12.5 up to 18, looks like we're going to increase by 5.5. All right, let's check that out. So first differences are different. So let's go ahead and check on those second differences. How do I get from 2.5 to 3.5? We are going to increase by 1. 3.5 to 4.5, increase by 1. If we get from 4.5 up to 5.5, we are going to increase by 1. So this does have second differences, which makes it a quadratic function. Comparing linear, exponential, and quadratic functions. Math with Mr. Williams. Example 4, writing a function to model data. Write a function that models each set of data. So we have a set of order pairs. By looking at those order pairs, we notice certain key aspects, that being the zeros. And seeing that it has a y-intercept and 2 x-intercepts, we have to assume it's going to be a quadratic function. So in that case, we're going to go ahead and break this down. Since I do have both x-intercepts, I'm going to go ahead and write down our factored form, which is f of x equals a times the parentheses x minus r1 and parentheses x minus r2. So knowing that our two numbers for our x-intercepts are going to be sitting at the -1 and the 2, we're going to plug that back in, giving us a parentheses x plus 1 and x minus 2. Now using our y-intercept, We're going to go ahead and plug in our numbers, giving us the -4 for the f of x equals a times, in this case, 0 plus 1, and 0 minus 2. This gives us -4 equals the a value. 0 plus 1 is 1, and 0 minus 2 is -2. We multiply out the right, we see -4 equals -2 times that 1 gives us a -2a. We divide by -2 on both sides, giving us 2 equals our a value. So let's go ahead and plug that back in now. So now we have f of x equals 2 times parentheses x plus 1 and x minus 2. We're going to go ahead and use our FOIL method, leaving 2 out front, and it'd be x times x gives us x squared. Then we have 1 times x is 1x. Then we have -2 times x is a -2x. And 1 times -2 is a -2. Let's go ahead and combine these like terms. Now we multiply everything by the 2 out front, and we arrive at our quadratic function. All right, let's go on to the next one. Here we have a table. We can see that our x values are increasing by 1 each time. We see we go 4 down to 1 for our y value. We see it's subtracting 3. Subtracting 3 again. From -2 to -5, it's another 3. And another 3. So this is going to be what we call a linear relationship, which means we can just plug in our format. Y equals mx plus b, and we know our y-intercept's at a -2, so that's pretty easy to identify. And then we know our rate is at -3, and then we just bring in our variable. So now we have our linear function written out. All right, on the last one. And we can definitely tell by looking at this, this is going to be a quadratic relationship here. So the choice is, what do we want to use? There's different forms for it. We have our standard, we have our vertex, and we have our factored form. So let's go ahead and use, in this case, since we know where the vertex is, we're going to go ahead and use that format. Okay, so we have f of x equals a times parentheses x minus h squared plus the k. And we know that our vertex is sitting at 0, 0. So we'll go ahead and plug that in. And this basically cancels out the k at the end. And since x minus nothing is just x, we end up with ax squared. All right, let's go ahead and just pick any point that we like. I don't really care for the ones that are midway through the box, so I'm going to identify this point right here, and that's going to be at -2, -12. Let's go ahead and plug that number in. So our -12 is going to be our y value, or f of x value. And our x value will be a -2 squared. So -2 squared is going to give us 4. And we want to cancel out the 4, so we're going to divide by 4 on both sides, giving us a -3 as our a value. So then we go back and we write our quadratic function out as -3x squared.